We're going to discuss a brief derivation of the Doppler effect. Now, we should start by stating some important limitations, the first of which is that we're dealing with a system which has a medium. That is, for instance, sound waves in air. That's the standard way in which we observe the Doppler effect, the typical examples being something like an ambulance siren. And in this case, you see that either the source of the sound or the observer moving changes the observed frequency. So we're just moving. And we'll derive the Doppler effect for both of these cases. So let's start with the observer moving. In this case, if the observer moves towards the wave source, then the observer will encounter the wavefronts more often. The wavelength will be unchanged, but both the velocity and the frequency appear to increase. So lambda, we will say, is fixed, but both v and f appear to increase. Now, what does this mean? Well, in particular, the apparent velocity with which the waves approach the observer, so I'm going to call that v prime, is going to equal v, the velocity of sound in the medium or whatever the waves are, plus VO, the velocity of the observer. Notice that using the signs that I've chosen here, the observer moving towards the source is positive. So I will put down V observer positive. Actually, let me just change that and make that a little bit more obvious. Positive when towards the observer. Oops. So, what does this mean for the frequency? Well, we have that the apparently observed frequency is going to be v prime divided by lambda, the wavelength, which hasn't changed, and that's just v plus VO over lambda. That's a perfectly reasonable formula. However, we normally want to have the frequency which is observed in terms of the original frequency, the frequency emitted by the source. So we're going to scale by just v over v, which is of course 1. The reason we do that is because then we can take the v and the lambda and combine them into a frequency. So I'll change that, and we have v plus VO divided by v. That's taking the top, the numerator of the first fraction, and the denominator of the second fraction, and we're going to multiply that by v over lambda, which is of course v plus VO over v times the original frequency. That is the standard formula for the frequency for a moving observer. You can of course divide top and bottom by v to get 1 plus VO over v. So I'll shift to a new page. And we'll now think about the moving source. The moving source is just a little bit trickier. It's not much different. When the source moves, effectively what we have, and I'll draw this terribly badly, is we have a source moving towards the wavefronts, and so in the direction of the source you can see that the wavefronts bunch up, and so obviously the source is moving to the right in this picture. I have not given myself enough space there. Obviously when you're writing answers you should give yourself enough space. So the observed wavelength changes. So lambda prime is given by the original wavelength, and now it decreases if the source is moving towards the observer. So we have to subtract something off that, and what we subtract off is the velocity of the source multiplied by the period, that's capital T. And this little formula here, VST, is the distance travelled in one cycle of the waves. So now remember that T is actually equal to 1 over F, and so we see that we have lambda prime is equal to lambda minus Vs divided by F. Okay, again, that's a reasonable result. but we need to have it in terms of frequencies. So now we recall that lambda prime and lambda can be related to frequency, so we find that we have v over f prime, so that's lambda prime, is equal to v over f minus vs over f. So in order to simplify this and to bring the frequencies onto the top, onto the numerator position, we'll bring the f prime on the left-hand side up onto the right, we'll take the f on the right-hand side onto the left, and we will divide through, and we'll see that we get f prime is equal to v divided by v minus vs. So that's taking the v minus vs on the right-hand side of the equation, moving on to the bottom of the left into the denominator of the left, and that multiplies f. If both are moving, if both source and observer are moving, then you combine both the changed velocity and the changed wavelength. So we see that f prime is equal to v prime over lambda prime, which is equal to v plus vo divided by v minus vs, but remember that v minus vs is divided by the frequency there, so that's just gives you v plus vo divided by v minus vs times the original frequency. So there you have a relatively simple set of the derivations for the Doppler effect. In both cases, you're just thinking about the effect of the motion, either of the source or the observer, on the wavefronts, and how that's going to change the observed frequency or wavelength.